Hello everyone, this is Breaking the Ankh Deterministic Propagation Netcode in Spelunky 2. Please remember to silence your phone, fill out the feedback form, and enjoy life. To introduce a bit myself, I'm Guillermo and I've been balancing the last 5 years of my life with working at BlitWorks and helping as part of the teaching staff of local universities, where I try my best to improve the system from within. I consider myself an in perpetual training problem solver who happens to be working on his much overdue master thesis and enjoys creating and experiencing all kinds of fiction. I'd also like to introduce BlitWorks. We are a medium-sized studio specialized in high-quality game porting that does a bit of publishing and co-development. We have been very lucky to work with incredibly talented developers from all over the world on awesome indie titles, including the original Spelunky HD port. Also, I'm very thankful to the whole BlitWorks team for being a great community and to management for providing me the extreme flexibility needed to contribute mentoring students and new developers at both Open University of Catalonia and University of Barcelona. Now, for all of you who aren't familiar with the Spelunky series, Spelunky is a precision platformer run-based game designed by Derek Yu. In Spelunky, each run is different due to changing room layouts, and there is no progression. Because of this, the focus of the game is put on the player, who is changed through the emergent stories, experience it on each run, and well, each run will also provide a lot of knowledge and practice. More specifically, Spelunky 2 introduces a lot of novelties to the series, such as real-time liquid physics and online multiplayer. You can get more information about Spelunky 2 in Derek's Yu talk. I'd also like to introduce these talk goals so that you can identify if it is interesting for you. This talk is about how the online stack of Spelunky 2 works. It's about the problems we didn't expect, the netcode, the servers, the decisions, and the problems that surprised us even after doing our homework and reading all previous literature and watching related talks. More specifically, we will try to avoid the topics related to determinism problems, optimization, clock drifting, and general engine design that previous talks covered in detail. So let's start from the beginning. After being introduced to the project, the top priority was evaluating the situation, the constraints, and getting familiar with the code base. The most significant constraint was probably that we wanted to keep the world as alive as possible, so in order to do so, we decided that everything should update without camera-aware optimizations. This would limit a lot us into what kind of optimizations we could do. Also, a possible arena mode had to be as fair as possible, and because it's a punishing precision platforming game, we wanted to minimize input delay and target a local multiplayer field without nonsense interpolations and following game mechanics. I believe this led the team to decide that rollback netcode would be a perfect fit, and it makes a lot of sense. Next were staffing constraints, because the whole game, including work done on all 3 supported platforms and the 53 patches to date, were around 8 man-years of engineering work, and maybe at its 1 week peak time, we had around 4 concurrent engineers at peak. So that meant that not a lot of resources can be dedicated to a side feature such as online multiplayer. So using other solutions would have significantly increased engineering man-years or maybe even delayed the game. Also, keeping up with the constant changes, which were on average around 60 changes per patch with a weekly patch, would have been a bit insane. There were also codebase constraints. Spelunky 2 codebase, as far as I know, tries to keep the feel of Spelunky HD, while providing online mechanics and a testbed for new mechanics and features Derek Yu wanted to try. This in itself leads to a very flexible codebase that isn't very cache-friendly. However, performance profiling didn't look as bad as to raise any alarms. thought it was definitely in need of work. Early on, replays were introduced to guarantee that the required amount for rollback netcode, the required amount of determinism for rollback netcode was provided. This combo of replays and determinism is very powerful, and we have used it in multiple projects. Replays will show up again later in the talk, but I'd recommend everyone who hasn't watched the Retro City Rampage talk on the topic of replays and automated testing to watch it. Other than that, the existing netcode didn't work out of the box after laying around for around 3 years. And considering how small it was and still is, we decided to redo it in order to be way more familiar with the code. So before getting to the meat, let me provide a sales pitch of rollback netcode. Rollback synchronization is a technique that, given enough compute time and a deterministic update function, keeps in sync any game without worrying about mechanics, latency, or cheats. In most reasonable network conditions, players will feel exactly like local multiplayer. Also, programmers will be able to program the online multiplayer as if it was a local multiplayer game. So that's obviously great. Not to mention the point of cheating not being really possible without the agreement of all participating players. So, well, I mean, it's perfect. That will be everything. Thank you for coming to my GDC talk. You can buy rollback netcode shirts in the gift shop. See you. But wait, hold it. Stay around for a bit longer. Before closing the case, let's see how rollback works. Rollback is based on a deterministic approach to netcode. Deterministic netcode is built on a design where each possible state is the result of running the update function with a specific input, game state, and time step. For this to happen, a lot of considerations must go into developing the game, including avoiding the use of system calls, CPU instructions, and events, and more things. I mean, previous talks have done a really great job explaining this. So for the specific case of rollback, we use this property to predict the state assuming unknown inputs will be unchanged. And when our prediction is wrong, not if, when our prediction is wrong, we roll back the state to the last good known prediction and rerun the simulation. This means that for this to work, we need to copy and store multiple copies of the state. So now that we have seen a bit more, let's talk about the negatives. First of all, in order to process a rollback of a given amount of frames, that many frames should run in a reasonable amount of time. Also, because multiple copies of the game state needs to exist in the heap, this means that the game must make copies and sometimes restore previous copies. This is what causes memory to become entangled with space, and the whole memory space trade-off stops being a trade-off. Also, because it's built so heavy on determinism, this means that information can be hidden from the clients. It's not important at all for Spelunky, but it might be in other games. The game also needs to run deterministically in all platforms, and that will take part in multiplayer, and this is no small feat. And finally, it's worth mentioning that the resource management becomes much more complex when working with rollback netcode. With all this context in mind, we started optimizing the game, because maybe 3-6 frames in 16 milliseconds aren't enough for rollback after all. That would give us around 64 milliseconds of flawless latency support. But would that be enough? We knew it wouldn't be enough, so in order to investigate how to improve this, we did performance profiling, and we evaluated areas of potential improvement. The 4 main areas of improvement were entities in red, liquids in dark blue, memory overhead, which is light blue, and automated resource memory management. So the most interesting optimization surface, after all, were memory operations. As we have seen, rollback directly ties space to time. This is pretty bad for some kind of games such as Spelunky, as you can see in the blue portion of the performance stats. Roughly between 25 and 65% of the time, depending on mispredictions and the generated level, were spent on memory copies. This was especially annoying because memory usage had very little surface of improvement. Our lead programmer Mickey had always kept this in mind and the whole memory was very optimized with custom allocators and most data structures using small data types, bit fields, and also structured packing by hand in order to avoid padding. As such, a lot of systems, such as particles, run in the non-deterministic state in order to reduce the deterministic state size. And the memory copy operation also didn't have a significant improvement surface. So what do you do when a big challenge comes up? Obviously, you do nothing, move on to something else, and start looking for a solution to it. So we moved on. One of the first areas we tried to optimize was leakages. Leakage physics are one of the most delicate parts of Spelunky 2 due to determinism, performance, and the cost that, well, every single particle must update every single frame. So it's pretty heavy performance-wise. We had been using LiquidFun, a very nice library that implements particle-based liquid physics on top of Box 2D. Optimizing this made a lot of sense because we were running the liquid simulation in parallel to entities and a few other systems. So optimizing most of the code base wouldn't improve anything, as long as liquids were the bottleneck. It also meant that optimizing liquids wasn't going to solve the problem by itself, since then entities would become the bottleneck, but it was a good start. So we were trying to optimize liquids by moving away from particle-based solutions. For this purpose, we researched a lot of alternatives in order to get significant performance gains, starting with building our own vectorized backwards moving least squares material point method. And it was really fast, like 8 times faster for 10 times more particles. It also allowed us to play around with deformable materials such as snow and jelly. However, we ended up reverting to LiquidFun because at big granularities, the liquids didn't feel really right in grid-based methods, and at small granularities, were very frustrating because of the game mechanics of Spelunky. You could be killed by a bunch of lava that was very small and you didn't see, and it wasn't as clear as to when lava would kill you and when it wouldn't. Other alternatives we evaluated were LVM and cellular automata solutions, but due to the continuous movement of push blocks and moving platforms, in Spelunky 2, this would have required to discretize the space at a very small granularity, which would have added a lot of inconsistencies and other performance overhead. This in turn meant that we couldn't optimize liquids that much, so we had to optimize the automated memory management. It was pretty easy. We went ahead and made the cleanup process around 5 times faster by using a more cache-friendly data structure based in Robinhood addressing. And then you keep working, and one day you can call it day -403 based on release date. The idea of propagation netcode pops up. The deterministic propagation is essentially a rethinking of the relationship between lockstep and rollback. In order to explain this, I really like the analogy of time travel and multiverses. In the deterministic rollback model, it's as if you messed up the past, so you decide to go back, fix it, and return to the present to see a more synchronized world. With deterministic propagation, you instead are always living in the current universe, and then one day you just wake up at the start of your update loop and are in a different, more synchronized universe by magic. So implementation-wise, the main idea is to have multiple states that are updated simultaneously. So you have a first simulation that does nothing special, nothing syncs, and we know everyone's last input. We pick it and use it to simulate the next frame. So it's pretty much always wrong, but only slightly wrong. Then a second simulation exists, which is just a regular lockstep simulation that only knows the truth and waits for everyone's inputs before running a frame. And then, well, the information it has, it's always ground truth. Finally, we have at least one propagation simulation that forks the lockstep simulation and predicts unknown inputs until it becomes the new present, replacing the existing present with a more synchronized universe. So if we show this in a more visual format, we can see that there are multiple blocks that access fully independent memory and have different time constraints and a few interesting properties. This model mitigates the cost of resizing the game. The amount of state copies you need to keep around is drastically reduced to a constant value, regardless of the resigning window. It's much easier to multi-thread than rollback model, since by itself, each simulation can be using a different thread with different memory. And also, given equal compute power for each simulation, there is an equilibrium that guarantees that the propagator can catch up with the present. Also, because each simulation can run in a separate thread in a transient functional manner, cache is improved as less thrashing occurs and pretty much no locking is required except when swapping states. Also, it's pretty nice that only one operation per propagation is required, and this, because only one copy operation per propagation is required, it disentangles space from time, so it allows us to start trading off memory for time again. So to sum everything up, you can see here a totally unbiased objective comparison table designed by a committee of myself, of no one else, who is obviously not biased towards his own solution, comparing what I consider the ideal netcode features. So first of all, as you can see, netcode not based on determinism in the first column is reactive, and it's very implementation specific, so it must be customized for individual game events, mechanics, and entities. This kind of netcode requires a huge amount of work and care that grows with the game scope. So in order to provide a good experience, prevent cheating, and keep up with the gameplay logic and project scale, you need to add more resources to developing the netcode. Compare that with input delay or lockstep netcode. That only requires determinism and doesn't really have any extra performance requirements or extrapolation issues. It's a really good model for some genres, but the maximum delay before the game becomes unplayable is pretty low, especially with action games, so it's not perfect. Rollback netcode, on the other side, improves a lot by trading off performance, but it wastes cache usage and ties performance to actively used space. It can be mitigated in multiple ways and can be potentially improved with kernel support for only copying memory pages on write and mapping page by hand, but unfortunately, this is not available on most platforms. Finally, propagation netcode rethinks determinism in order to mitigate the performance requirements introduced by rollback, while also providing some additional features at a small development cost when compared to other solutions. And then, after talking a lot about this, we decided to do nothing. It was something that we believed it would be required if a Nintendo Switch version would ever be a thing. But since it required a lot of changes from the existing version in order to work well with our code base and fix the update so it had no side effects, we decided to stop working here and focus on other things. So we started working on that things that have nothing to do with the install. We talk with Sony, we work on the game, we decide to add support for about 60 Hz, which is something that doesn't play well with deterministic netcode and is often implemented either by increasing update rates or by having variable delta time. So we decide to go instead with a different solution. We decide to use interpolation in order to support higher update rates. This idea was validated through the creation of a prototype called Super Toad Boy Platformer that would run at 20 updates per second and be interpolated to arbitrary frame rates. It's something that works really great, and the improvement was very obvious and perceptible to the members of the team with 144 Hz screens. And even though it still has a couple of glitches, we think that this is a great approach to get most of the benefits from an increased refresh rate without increasing compute costs. Similarly, it would have been interesting to update most of the world, but the players at a rate of 10 to 20 updates per second while keeping the players at higher update rates in order to improve performance, but that would have required too many changes at that stage that could introduce unintended and unnoticeable change to gameplay that we didn't want to deal with at that stage of development. So we spent weeks meeting platform requirements, fixing bugs, and then it just launches on PS4. So the game is out on PS4. We are barely able to release the day one patch in time. And then we crash with the ugly part of rollback. We have seen the good, we have seen the bad. Now we will see the ugly part of rollback. Degradation. Rollback netcode and other determinism-based netcode that does extrapolation such as propagation itself degrades awfully. For freeze's sake, I can't even express in English how bad it degrades. So let me show this to you with a couple of videos publicly available, recorded on the day one. Okay? So you can see in this video how rollback works well. The character is juking a ghost. Everything works. Okay, it's a happy day for that player on day one on PS4. Here you can see a very different game. A game that is pretty much turn-based. A game that runs at most at 10 frames per second. As you can see, this is pretty bad and fully broken and unacceptable. Let's compare this with a simple interpolation I developed for a title called Full Metal Furies, released by Cellar Games. Just keep looking at the top right enemy in the left gift, and you can see the enemy in orange with the last known server position, and the enemy in regular sprite with the local position, okay? In this situation, there was very bad network conditions, over 20% of packet loss, up to 1 second of jitter. You can see how a simple interpolation manages to hide all of this in a way that isn't noticeable to players in the game. It just looks great, especially when you compare that to this. Okay, you can see that there are a lot of teleports that it doesn't seem to work well. It's extrapolation at its best. Okay, if you notice the difference, whenever determinism messes up or extrapolation kicks in, it goes very wrong. Okay, if determinism goes wrong, well, the game, each player starts playing a completely different game and nothing seems to make sense about the movement of other players. And if clock drifts due to extrapolation begins to go crazy and it's not very playable at all. So, well, that was the first day. We spent a lot of... we move on to the second day. We decided to stay awake until pretty late watching stream and identifying issues. We investigate and conclude that the issue is caused by very high latency locations to our server that we didn't take into consideration, and also to people who, depending on the internet's mood, had big latency spikes that made the game update spiral out of control, with simulation times growing with each frame. Okay, so you might be asking yourselves, how could performance spiral out of control that much? Well, Spelunky 2 didn't really take more than 1 millisecond to run a full update on a 9-year-old dev PC. So how did this happen? Well, it was due to a combination of cache, rollback, misprediction, latency, and core speed. Because the game is 2D, players will often assume that it shouldn't require much resources and it should work on all hardware. This is not the case at all for Spelunky 2. We wanted our world to feel alive. We wanted the player to ask, what the fridge happened here that there is this turkey dead? Why? What happened? Why is there meat there? I mean, it's that kind of things makes the experience much better. So this meant that the whole stage had to update its frame regardless of player position, which is in itself pretty challenging due to the sheer size of the fully destructible stage, real-time physics, dual layers, pathfindings, and collisions, not to mention that everything can interact with everything, and by interact I mean explode, freeze, crush, ride, or whatever you can imagine. Also, don't forget that the game has huge stages, with 2 fluffing layers. I mean, can you look at both pictures and say it's just one level with 2 layers? I mean, that's huge. That's one level, what you can see over here. So since changing the way that matchmaking worked to expand more regions wasn't trivial, we decided to work on a single-threaded version of the propagation netcode. So other cores are used by liquids and particles, so it's not really that the whole implementation was single core, but both simulation didn't run at the same time. Okay, so it should have worked fine as long as we could have pushed 4 updates per frame. And the main objective was fixing the turn-based Spelunky issue, but it turns out the additional memory copying kept it unplayable. After profiling the cost for running 4 updates per frame, with the copies required to replace the state for each simulation, we found out that some levels, such as Blood or Olmec, were clocking at over 30 frames per second, at over 30 milliseconds per frame. So at this point, we were pretty exhausted. We were thinking, whoa, this is bad. But in a last push, we managed to improve a lot the experience before publishing the last patch of the week. I believe it was the 7th patch. The 2 main improvements were abusing virtual memory in order to swap the game states without copying, and we also added another improvement by skipping the CPU cache using platform-specific functionality. So that allowed us to reduce execution time a lot. But unfortunately, it wasn't perfect yet. Okay, so now the game worked pretty well on PS4 against PS4, but because some frames didn't make it to the 16 millisecond barrier, this meant that in some situations, such as when one player was using a PS4 and the other was using a PS4 Pro, the performance would diverge too much. And well, we have a system that allows us to accelerate or slow down frames, but it has some limits in order to feel good, to make the game feel better. So, well, in these situations, the game was not able to catch up. Okay, what this meant, if you check the video, is that in some situations, the game would seemingly work well, and then when CPU was bored, the other universe would catch up with the present and replace the current one. You can say this is pretty bad. Fortunately, a lot of people were playing PS4, so it wasn't that bad to a big portion of our player base. But the problem was that a lot of friends were playing using different PS4 systems. So for them, all games would at some point, if they reach a deep enough portion of the game, be fully unplayable. Okay, so on a side note, from all the bad news, we were really happy that adding an option to peak input delay was a well-received decision. Okay, we believed from the very beginning that it was the right choice because everyone has its own preference. But we were worried it may cause a lot of a swarm of the same lag reports because of people lowering their delay to zero or increasing it too much, but it didn't happen. So this proved a good decision since different players have different preferences. For example, I don't care if the game has 1 or 2 or 3 frames of constant input delay. It's very important for me that it is constant. However, instead, Tony Cabello, BlitWorks CEO, didn't enjoy the game with more than 1 frame of input delay. And some people, like Colin Norway, the Blue Spelunker, were also very thrilled to know that they could disable all input delay, even if that meant having frequent extrapolation glitches, but a much better experience. A popular streamer of Spelunky 2 called Chanagir has been making a lot of content with pretty much everything Spelunky 2 related, including patch notes. And for example, he prefers to have input delay at the default value because it makes for a much better viewer experience in his Twitch channel. Back to the main topic, in order to get propagation fully working, we needed to make the game able to run multiple instances of the simulation concurrently. We needed each universe to do its thing. This was a problem as our update function wasn't made with this in mind. So it had a lot of side effects, and existing optimizations used shared data outside the deterministic state, which meant we couldn't make this really easy or fast. This meant that we had to make a lot of very small and deliberate changes so that everything would work well without crashes, race conditions, and all kinds of issues. So eventually we get a pretty solid playable version. It has multi-instance and you can play it with for at least 60 minutes without crashes. So we decided to release that preview version so that we can spot any unforeseen problems and avoid what happened on PS4. It was very useful. We received a lot of feedback and patched on daily basis using Discord to distribute the patches. Both using Discord and releasing a preview proved very useful. Using Discord gave us a tight control over who could play the preview through the use of roles that could be revoked when needed. And Discord also facilitated receiving feedback, sharing files, and updating the build. So in the end, deciding how many people and who and why we would invite to the preview was hard. We didn't know how many crashes due to obscure race conditions there could be. We didn't know how long it would take to get the game to a playable state for more than 10 hours. We didn't expect many problems, and the build was definitely playable, so we wanted to invite people that were very vocal and could complain about this, as to improve as many things as possible while we were setting up the new server fleet and adding some PC-specific features such as the Discord and Steam invites. Okay, so this led us to multiple inviting criteria, starting with everyone that had created something cool, such a mod, a modding tool, streams, videos, fan art, and pretty much everything, which ended up being a very good decision that would give them early material for their content, and also it had some unexpected perks for us, such as being able to watch a 10-hour stream at higher speed in order to investigate issues that happened or could happen. This also ended up building a lot of hype. Building a lot of hype has been a very weird experience. We'll see later how this was both good and bad for us. And well, we invited more groups of people. We invited a group that was already playing online. We wanted to improve their life, as streaming a precision platformer is a subpar experience. And it was very nice from them to provide us with feedback comparing our solution to compared to the streaming solution. We were also inviting some people that had somehow problematic setups, such as people that didn't meet the minimum requirements, people that didn't play on North America or Europe, and people who had very bad internet connection. All this helped us validate some of the most extreme and worst cases. And finally, we also wanted to reward users that were active on multiple communities such as Reddit, Steam, Discord, and Twitter. We believed this would be to the best of everyone's interest, because in the current world, it's very hard to keep up with everything that goes around, and communicative people that are honest and they express their opinion in all platforms without sugarcoating the truth are very helpful, especially when empowered with first-hand information, so that we can in some way be more transparent to our community. Also, during the preview days, we took one of the best decisions, adding the best feature I haven't seen praised enough in determinism talks. Imagine the following situation. There is a ghost issue that our awesome QA team at Lollipop Robot had tried to reproduce for a very extended period of time, at the sync at Olmec. However, no matter what they tried, it was impossible to reproduce the issue, and not much information was provided by the 7 PS4 players that had reported this issue. So after more than a month, we believed that it was the same issue that was affecting other players. The game just couldn't keep up. A month later, during the preview, 2 people, including one streamer that was streaming, had a full desync live. So after watching it, we went ahead and made a special build in a few hours with this specific feature and asked them to play again. 6 hours later, the bug was fixed. As you can see, the desync was a very heavy desync. This is the same frame running in both games. It's very early in the Olmec level, so it was where no one could reproduce it. Even more, after a whole month of time testing, fiddling around with settings, running automated tests with our AI player, etc. See, at this point, if you told me that it was caused because of a game setting such as a screen shake, I would have said, okay, makes sense. It's something we expect. It's something we are very careful with, but mistakes happen, so it wouldn't be surprising at all. Pretty sure everyone working with determinism has experienced something similar. But what if you told me that the code had already rolled the random number outside the branch? Well, at that point, I would have assumed that the screenshot wasn't deterministic. But why was it happening if the deterministic code was if the screenshot code was fully deterministic? Well, it turns out that at some point, the number generator we had this very common check. If you are rolling a random number and the maximum value is the same value or less than the minimum value, return the minimum value. This would mean that if you wanted to roll a number between 4 and 4, the result was 4. So why even bother rolling the random number generator? Well, of course, this doesn't apply to deterministic online multiplayer games. So the internal state of the random number generator would desync at this point. When investigating how this could happen, we noticed that this code comes from a very early commit, probably something we inherited from a previous title. From a previous title, meaning Spelunky HD. It was a little optimization that wouldn't matter in most code bases, but not here. So how did we manage to reproduce this and fix it within 6 hours? Meet ReplayTech. ReplayTech is an awesome piece of software, great for testing, iterating, and debugging. We also used automatic debugging for sniffing out determinism books, but that's a story for another day that should be told by another person. Network replays are crucial. It's something we had used in multiple earlier titles to do network debugging. The general idea is that at any given point in time, a replay capable of recreating the whole session can be sent to the development team. So if a bug happens with a properly working replay system hooked at a very low level, a single file can be sent to the development team that will provide all information needed to investigate the issue. These will make issues that are almost impossible to reproduce even after 2 months 100% reproducible, and will empower whatever the programmer is using. So he can, for example, live in a situation similar to the movie Groundhog Day in an environment with the bug. In that situation, it is trivial to allocate memory at a deterministic address and to assign a deterministic ID to stuff in the world, so that you know that freaky ghost with ID 37 on frame 42 causes a crash because of stuff. Furthermore, it will make each iteration faster, since you will know better each time you run the replay. You can do binary search. You can note down frames, IDs, and it doesn't require the reporter to try to find a set of specific steps or guidelines to reproduce an issue. No steps at all. It can be of help even to catch race conditions by rolling multiple times each frame, and if properly implemented, it also allows to swap between release and debug without losing information. Furthermore, because the developer has both the code and the replay, it's easy to check that the issue has been fixed by applying a code change at an exact frame and replaying the replay to see if the bug no longer happens. Honestly, if something in development could be called a superpower or cheat, it's this, and it's baffling that this tech is pretty much nowhere by default, especially when so many engines rely on virtual machines for script execution. So, while the preview was ongoing, we went forward with the plans to expand our server fleet, which we did in multiple stages. We felt reassured doing this as Glenn Fiedler kept thrashing out reliability at the edge, and we have had a pretty bad experience on previous peer-to-peer titles regarding host bandwidth and NAT traversal. So we started the preview with a single server in Chicago that was later, during the following 2 weeks, expanded to 14 servers pretty much everywhere in the globe. The positive experience that players of the preview reported, including popular streamers playing for more than 10 hours a session without any sort of crash or desync, were generating a lot of hype in the community. So we decided to rush a public beta so that everyone could enjoy an online multiplayer on Spelunky 2 before Christmas. As a side note for everyone or anyone trying to build a similar infrastructure as an indie, if you use a deterministic model for networking, you can use pretty much any server with a fair share of CPU time and good peering, regardless of RAM and storage. There are a lot of service providers other than Amazon Web Services, Google Compute Platform, and Azure, so be careful about bandwidth. Look for a provider that gives you a free coupon to test their servers, and check that they have helpful features for your use case. Some examples of helpful features are DigitalOcean's bandwidth pooling and Bolter shutdown after reaching a specified amount of bandwidth, which are great ways to avoid unexpected expenses. Regarding tech, our backends are C++ hot reloading dynamic libraries that run on FreeBSD. The whole reliability of the system that has 4 processes, including the server, is great, and even after more than 50 patches across 20 updates, during more than half a year, we have only had one partial interruption of service. Regarding implementation details, it's nothing too fancy. We are just batching a few received buffered syscalls to receive truncated data into fixed size buffers that are always zero-padded. The most interesting design choices are probably the leaderboard system that is designed so that clients fetch the whole leaderboard as a compressed blobs through content delivery networks, no complex API, and also the lobby matchmaking system, which is unreliable by design, so communication is performed by merging changes to a desired state structure that defines how the client envisions itself in the future. It works nice, it's easy to implement, it's easy to test, but it's a very bad model to provide meaningful error handling on lobbies. So was using a hosted service instead of peer-to-peer a good idea? For whom, you might ask? It provides guarantees regarding quality of services, allows players behind a symmetric node to play together, and makes crossplay easier. For deterministic games, it's also something that provides us an explicit timeline of events and makes it easier to compensate for latency. However, it's also very harsh. Especially as an indie, you can have someone in each time zone looking out for the fleet. So if any problem arises, you might take a lot of time to react. This didn't happen to us, but it concerned me to the point of waking up during weeks in the middle of the night with nightmares to check if the server was up. In the end, having an Android app to check the fleet helped a lot getting over it. Another frustrating point is that the player base becomes smaller on consoles because of gatekeeping. This is annoying because small games often don't have the luxury of having big player bases. So gatekeeping a portion ends up with way more dead online modes on consoles where no one is playing online, while on PC you can find 2 or 3 players if you wait a bit of time. This is the case for many small games, and it's even more frustrating when it's the platform gatekeeping players who paid for your game and they want to play on the servers we paid for. It's also a bit annoying because it's the path of most resistance regarding requirements. Going with independent servers and crossplay seems to be very biased and focus on free-to-play titles with in-app purchases or games that are full services with leagues, friend systems, party systems, ranked systems, etc. It's a pity that it has become so complex. We want crossplay so our players can have fun. We don't want account system. We don't want retention techniques, daily missions, in-app purchases. And definitely, we don't want to exploit the variable ratio and interval schedule of reinforcement to keep the player spending. We just want them to play with their friends regardless of platform. So the promised day comes, and we release the public online beta on Steam so that everyone can play. It was a beautiful day, a Tuesday the 13th. The sky was taking a beautiful orange shade during sunrise, and the day went mad. No, I'm not superstitious, but maybe we should have waited for the 16th. To sum everything up, first, multiple Google services went down. This was bad because that broke Discord rich presence, and Discord rich presence is what made the invite system work well. We didn't have this information at the beginning, so we were investigating what was going on. It was a catastrophe. Our money was on something we had recently added, dynamically assigning matchmaking servers based on quality of service to the matchmaking service. Fortunately, a very cool community member called Gary, who also has been developing a lot of stuff to mod Spelunky 2, happened to work at Discord that pointed to us that this could be the problem and it would be outside of our control. So we went ahead and did a pair of run-onlines before releasing the build. And then the Steam invite system had stopped working. It didn't make much sense. We had to investigate. However, because of the hype for the online release was huge, probably thanks to multiple streamers such as Chocolate Cake, Chanagir, Hectic, X, Twiggle, Tic-Tac-Toe, Ivyojari, and Noduro, and more were playing during the preview, and other players such as Akira or Redscam were also making videos of the multiplayer. So it was huge to the point that 30% of the message sent during all the lifetime of the Discord server, 3 months, had been sent that day. It was huge to the point we had to disallow all people without a special role to chat for an hour. So huge that we had 2 raids of more than 200 people. So huge that it was the day of the year that most people joined the server. So huge that emote reactions on message became a problem. So incredibly huge that even then, many players decided to buy Nitro and boost the server in order to get a special role and talk, effectively making our Discord pay to chat. So we decided to release a switch. It went wrong, Steam invites were broken, and lots of people couldn't join through Discord too. We had no idea of what was causing the invite problem. We investigated and investigated and investigated and investigated. We couldn't reproduce it, but there could. Why? At some point near 1 a.m., after trying to do pretty much everything, I happened to misclick the build event and ended clicking the rebuild event. Both invites on Steam and Discord were working again, and they didn't break anymore to this day. Obviously, some object of the build was corrupt, and for some reason, it didn't trigger a rebuild. It's something that every now and then happens, so we always do a rebuild before submitting a patch, but that day had been so chaotic with Google going down and all the moderation we had to do that protocols were broken and we paid for it. But what if I told you that that wasn't all? That at the same time we were investigating, people playing near Canada were having problems. What if I told you that after fixing that and waking up the next morning, we noticed some emails from our service provider for that specific server stating, hey, we are having a DDoS here. Either way, it was a fun, crazy day. In the end, all went good enough, so we can't complain. But deep down, sometimes I think, maybe we should have waited for Wednesday. So a few days later, we released the PlayStation 4 propagation netcode version, and the feedback is very positive, with expressions such as online on PS4 feels amazing now, and today I played with a friend and it was really the best time. The feedback from the PC version was also very encouraging, and this feedback was the best Christmas present that the community could have given us. So was adding online multiplayer a good idea? I don't think that multiplayer by default is a good idea. The rationale being that netcode takes a lot of time to implement, and you have to wait what the multiplayer will bring to the table against what you could implement in that amount of time. Of course, for games that rely on increasing LTV and retention, it's another issue. But from our point of view, it just may not be worth for all games. You may feel inclined to add it because it's requested, but keep in mind it will always be requested. It has been requested in Kerbal, Gone Home, and Life is Strange because it's a very appealing concept and each person has its own preferences. However, going that way, the stream of requests will never end. Matchmaking, boat kick, lobby browser, crossplay, player versus player, invite codes, friend list, reconnection, race modes, battle royales, progress, achievements, 8-player multiplayer, voice chat, text chat, quick chat, pinging markers, custom online controller mappings, LAN modes, more randoms in the online matches, which is something we can't even control. Drop in, options to customize online user interface, seeded online multiplayer, etc. It will never end. Also, we believe that the arcade view of online multiplayer is a good option. We don't want to optimize retention. We don't want enough purchases. We just want the players to go online and play as if they were using arcade cabinets with multiplayer and a leaderboard. And we believe that this approach for Spelunky worked really well. Enter server analytics. It let us measure big community reactions, such as when an awesome Korean streamer going by the name of Noduro invited viewers to play online. You can see the spikes in the chat, how a lot of players were in lobbies, but the amount of ongoing runs didn't change that much. In general, a server dashboard feels very satisfying to look at. Analytics have proven very useful in many situations, such as keeping calm when someone says that the server doesn't work, but there are 700 online players. It also helps scheduling patches in order to avoid in order to release them in off-peak hours to avoid inconveniencing our player base. And it allows us to verify that the bandwidth usage, that we avoided a huge bandwidth cost by using the right providers. Overall, we are really happy with our setup. It's understandable that some people assume it costs a lot, but for deterministic netcode, the needs means that probably costs 10 years of the whole fleet costs less than the average yearly salary of a junior game developer that just left college. So we believe it's a pretty reasonable and cheap price to pay in order to improve player stability and experience. Before Christmas, we also managed to squeeze in the last patch we wanted the community to have, invite codes. We believe that invite codes are a great way for communities to allow inviting through any platform, including things such as WhatsApp or people that are in offline modes. And it will also be very useful for crossplay. Two details worth mentioning are that the invite codes are automatically copied from the clipboard and pasted, and that we decided not to show the invite code by default so that streamers could keep a code room private when inviting specific guests. Moving on to the last big topic of the talk, problems. We didn't have much problems with determinism, probably thanks to the culture of determinism and a very small engineering team. However, extrapolation, working as intended, has been an issue. It has been brought on multiple GDC talks, and it's something that most people, including us, find unacceptable. Unfortunately, this can happen in rollback and propagation if under certain circumstances. Also, clock drifting of machines that don't meet the requirements was quite a problem and is quite a problem. However, the biggest problem of all, the most significant problem was and is the ambiguous feedback we received. So, ambiguous feedback. You may know this game called Chinese Whispers or Broken Telephone, and it feels a lot like that. I mean, the users try to communicate a problem they are having using the best description they can provide with the knowledge they have, and that tends to be the game design. The game crashed, the game whatever. The point of it is that you'll see all these words being used as if all words were perfect synonyms. You'll see people say that lag is stuttering, that clock drifting is crashing, that disconnections are sluggish, that input delay is the same. All combinations are possible, and it makes very hard to know what problem a user has in order to help the user enjoy the game. So regarding other open challenges, one of the open challenges we are still facing is, as mentioned before, extrapolation. It's something we are considering addressing by adding some sort of output delay. We believe that buffering the last n stage of remote client and then using a past state to render the remote players might mitigate enough this to actually remove input delay in a non-competitive mode where other players' positions doesn't need to be that accurate. Also, regarding matchmaking, we have been running A/B testing comparing global matchmaking on PS4 versus regional matchmaking on PC. And this has been going on for a few months, and we are still unsure of what approach is the best approach. Regional matchmaking provides a great experience, but creates fragmentation. It's hard to find a match of peak hours, so most users rely on the Discord server to find a match that may provide a worse network experience. On the other side, non-regional matchmaking makes matchmaking actually useful, but every now and then we receive sporadic complaints of people that found a match with someone on the other side of the world and had a subpar experience. It's something we are still debating about, and in the end, the best solution might be mixing both so player can fall back to a global matchmaking. Another open challenge is how to handle computers not meeting minimum requirements, because you can lower the resolution to almost zero with pretty much any PC supporting DirectX 11, be it through an integrated graphics or dedicated, can actually run Spelunky 2, even way below minimum requirements. This means instead of 4 cores, a single core Pentium 4 computer. We have seen this in real life. So we have a lot of players unable to enjoy online because of hardware. Keep in mind that this is not exclusive of potato PCs, but also happens to laptops running on battery. Happens to desktop PCs that just got the latest Windows update. Happens when one computer has only one fast core and the rest of the cores are very slow. And happens to high-end Intel laptops that can sustain boosts for only a very short amount of time and then throttle a lot. External programs that show notifications also sometimes cause lag spikes, frame drops, and sporadic extrapolation teleports. It's something we detected early in 2021, and we're still considering how to approach this, as we were able to conclude without a doubt that 32 of the 36 cases in which players were seeing constant teleports were caused by this. It's a big problem for us because other than detecting this reliably, it doesn't seem to have an obvious solution, as micropausing would actually hurt a lot precision platforming. We could also slow more the game below 57 updates per second, but it may throw experienced players out of rhythm, and it may be exploitable in Arena. We may be able to show this information in the HUD, but it could cause discrimination. There are also many unexpected interesting findings. One of them was that roughly 8% of players experienced internet microcuts of more than 3 seconds. We didn't see this coming, and we have found a variety of reasons for this. Cheap routers, Wi-Fi adapters performing background scans, and ESP service microcuts. We plan on increasing the disconnect windows, but we first need to find a way to mitigate the damage that PC not meeting requirements could do in these situations. Also, regarding crossplay requirements, we didn't expect platforms to be so focused on one-size-fits-all requirements clearly designed for in-app purchases and games as a service that doesn't fit at all indie games. We would appreciate if this was revised in the future, as the requirements are an overkill for an arcade-like online multiplayer. Finally, we found out why many people couldn't connect to any of the 30 servers. It wasn't because of network problem, but because of players not following modest instructions. It caught us by surprise, but finally it made sense why some layout bugs that were fixed in the past kept happening and being reported. On a separate note, modding can cause these things. We haven't been able to analyze this in depth because of how time-consuming it is, but 2 out of the 3 early long investigations of hard things in the wild were caused by mods. Still, modding is great. We announced that we would evaluate it early on, and our plan was to fix up some bugs, then evaluate it. However, because of all the problems that came up while developing the online multiplayer, we didn't manage to do this in time, and somehow a full-blown modding community with more than 800 mods became a thing before the online was released, and with no tools and a lot of reverse engineering work. We are sure that mods are here to stay, and while it's low priority, we want to integrate mods with online in a safe way. for everyone. But right now it's Will West. So this will be everything. Thank you for coming to my GDC talk. I hope you have enjoyed the talk a lot, and feel free to ask me whatever. Have a good day.